Okay, you can start.
Thank you very much. Okay, I would like to thank very much the committee of organization and the scientific organization for this conference, and I would like of all my heart that the all the world in the all the words in the world in as soon as possible, especially in Gaza and in Ukraine. Okay, today I will talk a little with you about this presentation um, on the Brody hyperbolicity and the relation between it and the Kobayashi hyperbolicity. And I will study also the case of the hyperbolicity of the complement of arrangement of complex and real hyperplanes in the complex projective space. Uh, I have divided my talk into two parts, history and preliminary, and then the main some main results. Okay, in fact, I will start the I will start with the Kobayashi hyperbolicity. The theory of hyperbolicity, for the moment, in the sense of Kobayashi, is a way introduced by Shuichi Kobayashi in 1967 to test whether a connected complex manifold is hyperbolic. He is interested in the way that certain and some geometric object curve. This is a list of some reference. To see more and clearly the situation, this image indicates at the right hyperbolic space, in the middle the normal and Euclidean space, and on the left elliptic space. Now, to motivate little our situation, the hyperbolicity of the complement of arrangement of projective line in the complex projective space has been the subject of numerous studies for many years. So, for example, Emily Picard in 1879, he showed that any entire curve that avoids at least 2 points is constant. This is so beautiful. And this is mean also that any holomorphic curve from C into CP1, the one-dimensional projective space, avoiding 3 points is constant. Now, this last one has been generalized by Marco Green in 1972. Yeah, he showed that every curve from C into CPN, which avoid 2n plus 1 hyperplanes in general position, is constant. And I make that this is the definition we will say next, we will show next of the real hyperbolicity. Now, after 4 years of the theorem of Borel, Edward Borel of Green, excuse me, Edward Borel in 1976 showed that every non-constant it sure cannot be constant curve, because every non-constant application curve f from C into the two-dimensional vector space avoiding four hyperplanes in general position lies in one of the diagonals. What does mean diagonals? We have four complex hyperplanes. The application cannot be constant as green because we have 4 and not 5. Now we have 4 lines L1, 2, 3, and 4 as shown in the screen. We have 6 points, double point, S1, 2, 3, 4, 5, and 6. So the diagonal is the lines passing each from 2 double points from this configuration. So we have 2 double points, 3 lines, excuse me. Now, we have, which is beautiful, that we have generalized this result of Borel from 1976 in higher dimension. We take 2 hyperplanes in general position in the complex n-dimensional complex projective space. So we show that exactly there exists 1/2 Cn to n diagonal, and we have given the definition of what does mean a diagonal, such that any non-constant holomorphic curve f into CPL, which involves this configuration of two hyperplanes, there exists for each curve a cut f dependent of f, such that f of C is a subset of delta kf. Because of this theorem, we can easily prove the Greener theorem. I can save the page. The Greener theorem is that one. Any holomorphic curve that avoid 2n plus 1 hyperbola in general position is constant. How can we show that using our theorem? Imagine that we have a function f into the n-dimensional complex projective space avoiding 2n plus 1 hyperbolas. So suppose that it avoids the h1 to h2n. So by this theorem, f is included in one of the delta k, the diagonal, which is a line. Now, also f avoids h2 until h2n plus 1. So f is also included in another delta k. So f is included in the intersection of the two delta k1 and delta k2. So, which is a point, and this is how we prove that f is constant. So we prove easily the theorem agreed, because it was proven in 3 or 4 page. Well, as preliminary of my talk, I remember the distance of Poincaré. If V is a tangent vector 2D in a point Z, its hyperbolic norm is given by this formula. And we show that we recall that the unit disk dd of the complex plane D is equipped with the Poincaré distance, the next formula. The minimum under all the minimum of all the hyperbolic length under the curve lying or joining Z neo to Z1. And the hyperbolic line length of a curve gamma is given by this formula. Well, I present to you now the very famous pseudo distance of Kobayashi, and using it, introduced by Kobayashi in 1976. So, using this Kobayashi pseudo distance, we can know if a manifold is Kobayashi hyperbolic ordered. Let X be a complex manifold or X and XY in X. A Kobayashi chain joining the 2 points X and Y is given by the 3 sequence. Fe, sequence of holomorphic curve from the unit disk into X, and a finite sequence of Pe on X and alpha E on D, such that X equal to P neo, Y Pn, and for every E over I over 1 and n Y minus 1, we have Pe in this intersection. To see clearly what I have said now, we give this image. Imagine that we have a manifold X. We have X and Y. The idea of Kobayashi was the next. We take X equal to P0, P neo, and a sequence of Pe between X and Y, and Pn equal to Y. Now, the idea was to calculate just the distance between X and Y. We have to measure the distance, the small distance P neo, P1, P1, P2, P2, P3, and Pn minus 1, Pn, which is Y. Now, to just calculate the distance between P0 and P1, it will be calculated by pullback in the unit disk using a function, the sequence a function fi from D into X. Because in D, we have a true distance, which is the distance of Poincaré. Now, we define the Kobayashi distance as the nth under all the chain of Kobayashi we have just talked about of the distance between X and Y. So the distance between Fi minus 1 of Pe minus 1, Fa minus 1, the pullback of Fi of Pe. We have the sum of all these small distance between Pe and Pe plus 1, and then X here is said to be Kobayashi hyperbolic if the cop is a true distance. Well, we talk now about the Brody hyperbolicity. We say that a complex manifold X is a Brody hyperbolic if every holomorphic curve from C into X is constant. Very well. For example, D is a Brody hyperbolic. Using imagine that we take a function f from C into D with profit, but D is bounded. Now, using the theorem of Liouville, the function is constant, so D can be said as a Brody hyperbolic manifold. Now, X equal to the n-dimensional complex projective space minus 2n hyperplus in general position. Is not Brody hyperbolic because we can show that this X contains the complex line C. So because it contains a complex line C, so it is not constant. Now, as a remark, a complex Kobayashi manifold is Brody automatically, Brody hyperbolic. The converse is true except for compact manifolds. So this leads us maybe to our main result. Summary of our result that we can take into consideration. Okay, the complementary, the first one, the complementary. This is so strange. I thought that it's a theorem a little strange for me. The complement of 5 and infinitely many complex hyperplanes in C3 is not hyperbolic. Is not Brody hyperbolic. We can say is not Brody or Kobayashi because I think we are in the case of compact case. So we have equivalence. Anyway, that means that any application curve, any curve from C into C3 can avoid an infinitely many complex hyperplanes without being constant. This is very very straight. I will say we will see that after this theorem. In fact, as a sketch of the proof, if we take the hyperplanes in C3 in standard form H123 as Zi equal to nil, H4 like that, and H5 given by this set, we take A1 Z1 plus A2 Z2 plus A3 Z3 to just have a general position configuration. Well, now, since F avoid this configuration of 5 complex hyperplanes, that means that there exists, it avoids in particular H1, H2, H3, it avoids Z1 equal to nil, Z2 equal to nil, and Z3 equal to nil. So there exists a normal curve H1, 2, 3, such that our function f equal to a exponential h1 exponential x2 exponential x3. But since P de f will avoid P de he, then P of f is then constant by grid, because P circ f will avoid in CP2 a configuration of 5 complex lines which are P de he. Now, by grid, it will be constant. That means that there exists omega 1, 2, 3 different to Leo, such that for all that in C exponential, we have this notation because we are now in the complex projective space CP2. Exponential h1 2 point, exponential h2, exponential h3, it is constant. It's equal to omega 1, 2, 3. We can now divide by, for example, omega 1. So we have 1 exponential h2 divided by exponential h1 equal to 1 omega 2 divided by omega 1 and omega 3 divided by omega 1. This means that exponential h2 is equal to this constant omega 2 divided by omega 1 exponential h1 and the same case of exponential h3. So finally, the final expression of f is exponential h1, c2 exponential h1, and c3 exponential h1. This is not a constant. This is not a constant curve. Okay. What does that mean? This means that this complement, even of an infinity of hyperplanes of C3 is not a Brody hyperbolic, because we have found an application which avoids these hyperplanes without being constant. And we can show also that there exists L, a complex line, such that G of C equal to is a subset or included in this N. Well, this theorem now, we take, instead of taking 5 complex lines in general position, we take 4 complex lines in general position and a real subspace of R6 of real dimension 5, which is strange now that we can show that there exists a complex hyperplane C3. This is normal, denoted by H tilde, and included in H such that if the configuration is in general position, then every holomorphic curve that avoids this form hyperplane HE with the and our H real subspace of real dimension 5 is equal to avoid this configuration. Any holomorphic curve avoiding this configuration, it is constant. So I found strange that we can avoid an infinity of hyperplane in C3 and without having a constant function, as we have shown here. We have shown that we just found a function that avoids an infinity of hyperplanes in C3 without being constant. But if we take just 5, an arrangement of 5 lines, 4 which are complex, and 1 it's a real subspace of real dimension 5, so we can say that this configuration is Brody hyperbolic. So in this case, we have no Brody hyperbolic because we have found a curve and we have calculated that is not constant. Now, here in this configuration, we have no need to have an infinity of hyperplanes to deal with. We deal just with 4 hyperplanes in complex line in C3, and with a real subspace of real dimension 5. I think I have more time. I think I just here say that the condition of having a real subspace of a real dimension 5 is a optimal condition. Okay, I think I have no time because I have passed the time, but I take 2 minutes just to explain that if we change the real subspace of dimension 5 by a subspace of dimension 4, no the same we haven't the same case of as this excuse me as this theorem. So which means that any holomorphic curve can be constant. So the condition of having a real subspace of real dimension 5 is an optimal condition to the Brody hyperbolicity. Thank you very much.